we have talked a bit about messages and in principle how you can send them, what they are conceptually, but we're actually going to talk about some real syntax. So this is really the core of MPI. Obviously, message passing, sending and receiving messages. So a message contains a number of elements of some particular data type. So as I said, your canonical MPI message is 4 integers or 6 double precision, 6 doubles. MPI has basic types and derived types. Now we'll see later on you can build up more complicated objects which may correspond to C structures, or as Fortran calls them, derived types. And they're built up from basic types, but fundamentally we'll talk about basic types. So we'll consider at the moment you want to send a message comprising integers or double precisions or floats or something like that. Now it turns out that in MPI there is only one send routine. What I mean by that is there's not MPI send integer, MPI send float, MPI send double, MPI send character. There's MPI send. And that means that you need to tell MPI, because MPI is a library, you need to tell MPI what the data is, because languages like C and old-fashioned Fortran at least don't carry through type information. So when you call an MPI routine, you have to tell MPI this is an array of floats, this is an array of integers. So you have to pass a flag. It's just a value, a constant defined in the header file, which tells you what that data type is. And obviously this is one of the few places where MPI differs between C and Fortran. So for every basic type in the language, MPI has its own constant, and this will become a lot more obvious when we see some specific examples. But just for the moment, if you want to send a double in C, you have to tell MPI it's of type MPI double, which is just some magic number, some constant defined in the header file. For scientific and technical programming, I suspect you only ever use MPI int, MPI double, and maybe MPI char. C's got a lot of types, but only a few of them are useful for scientific and technical computing. So in Fortran, because the language types are different, we have integer, real, double precision, complex, logical. Then the types, so we have MPI integer, MPI real, MPI double precision, MPI complex, MPI logical, and MPI character. Again, for most programs, you'll use MPI integer and MPI double precision. I would say that for Fortran programmers, I would avoid sending around characters. Character arrays are weird in Fortran. So you have, yeah, so I would avoid that. It causes a bit of a work, but I mean, other than that, we're fine. It's the different Fortran, an array of 6 characters in Fortran is different from a character variable of length 6, and that's where the confusion comes. But this will become a lot less mysterious when we talk about real examples. Point-to-point communication. So, just to recap, point-to-point communication is a communication between 2 processes. It happens within a communicator. As I said, whenever any MPI routine, any communication routines takes a communicator as an argument, which defines the communications world in which it takes part. Now, by default, we'll always be passing MPI com world, which includes everybody. But we'll see later on that you can divide, you can split communicators up. It's one of the strengths of MPI that you can take a communicator and split it into 2 halves, and then those 2 halves become different communicators and are different communications worlds. But for the moment, let's just think about MPI com world. The source process sends a message to the destination process. The source process has to call a send. The receive process has to call a receive. The communication takes place within a communicator. So you can't communicate without to a process which is outside of your communicator. But again, because MPI com world contains everybody, that's not an issue with MPI com world. And the destination process is identified by its rank in the communicator. So your rank is really your key, the key thing you need to know. So point-to-point messaging in MPI, just to get some terminology, the sender calls a send routine. You have a number of options, specify the data that is to be sent, and this data that is to be sent is called the send buffer. So the sender calls a send routine, specifying a send buffer. The receiver calls a receive routine, specifying where the incoming data should be stored, and this is called the receive buffer. So you have a send buffer, which is your send array, and a receive buffer, which is the receive array, and the data goes into the receive buffer. The important point is, though, that metadata is describing the message is also transferred. So when it's like the message envelope, it will include information, we'll see later, like where the message came from, how long it is. So this is called the status. So when you send a message in MPI, you just specify a send buffer, and MPI constructs the metadata, the header information for you. When you receive data, the data goes into the receive buffer, but you have to receive the metadata separately. So when you issue a receive, you have to specify two storage locations, one for the data to go into, which is the receive buffer, but also somewhere for the metadata to go into, which is a small variable or array called the status. So send buffer on the send side, on the receive side, receive buffer and status are the key concepts and terminology. So we talked about communications modes in the first lecture about concept. You can send a message conceptually. You can send a message synchronously, which is like making a phone call. So you pick up the phone and the message isn't transferred, the data isn't transferred until the receiver also picks up. It's called synchronous because you're both on the line at the same time. There's a synchronization between you. Or you can do an asynchronous send, which is like posting an email, posting a letter or sending an email. How do these map onto MPI? Well, MPI has synchronous send, which only completes when the receiver is completed. And actually, that is just like making a phone call. MPI also has buffered send, which always completes unless an error occurs irrespective of the receiver. Buffered send maps onto asynchronous send. So MPI calls synchronous send, and it calls asynchronous send, buffered send. So one thing, why does MPI called asynchronous send, buffered send? Just think what's happening here. I've got some data, an array of a megabyte. I tell MPI, I want you to send this message asynchronously. I want you to send it off and just return control to me straight away, and I'll go away and carry on, doing something else. Don't tell me if or when the message arrives. So I've got a megabyte array, a big array. I tell MPI to send it. Let's call it X. Sometime later in the program, what am I going to want to do with that array X? I've declared a big array, and I've now sent it off somewhere. Sometime later, what am I going to want to do with it? Am I going to leave it untouched for the entire length of the run of the program? What am I likely to want to do with it? Use it again, exactly. I want to use it. Sometime later, I'll say I need to reuse it or update it. But if I don't know if and when the message has been transferred, how can it be safe? How can I safely reuse the buffer if I don't know if the data has been sent yet? What is the only way that the MPI library can implement asynchronous send safely? What does MPI have to do to implement asynchronous send? Think about it. Here's some data. I'm going to reuse it sometime in the future. You're not going to tell me when it's safe to reuse it, but I want you to send the data. What's the only way you can actually do that? Copy it, exactly. Copy it. So Jamestown, copy the data. That's why MPI calls asynchronous send buffered send, is to make it obvious to you that MPI is buffering the message somewhere. It is taking a copy of the message. And if you think about it, there is no way to safely implement asynchronous send unless the library takes a copy. So that's why MPI calls asynchronous send buffered send. Receive is always synchronous, completes when a message has arrived. So if you issue a receive, you wait forever. It's like standing by the phone for a phone call from your partner, or you've been on a date and the next day you're waiting for the person to phone you. In MPI, if they never phone you, you stand there forever. You wait forever. There are no timeouts in MPI. So that's clear. Synchronous send is MPI calls synchronous send. Asynchronous send, MPI calls buffered send, to make it obvious to you that MPI is taking a copy, and receive is called receive. Now, the confusing thing about MPI is that most MPI programs you see will use standard send. It's the standard thing to use. However, it can be either synchronous or buffered, and you don't know what. That causes endless confusion. So for the moment, when I say send, in this course, if ever I say call send, I mean call synchronous send, because we know what it does. And I have a lecture, the last lecture today, will talk about why people tend not to use buffered send and what the technicalities with standard send are, and why MPI thinks it's a good idea to make it either synchronous or buffered without telling you which. But to keep things simple at the moment, when you program with send, you should program with synchronous send, because we know what it does. It's like making a phone call. So the sender modes, standard send is MPI send, synchronous send is MPI send for synchronous send. As I said, this is the one you should use in all your examples, although real programs will tend to use MPI send. I'll explain why when you're learning MPI, you should use MPI send. Buffered send is MPI send, and receive is MPI receive. So in the exercises from now on, unless I say otherwise, I expect you to use MPI send and MPI receive. So send a message, this is the prototype, int MPI send, buffer, this is the send buffer, count data type, might be 5 integers, destination is where it's going, the destination rank, tag is an extra piece of information, we'll talk about tags later on, and the communicator, MPI com, the communicator in which the communication is taking place. For the moment, we'll just use MPI com world. Exactly the same for Fortran, buff count data type dest tag com, except we have the IARA variable. Now in C, these things are parameterized, so the data type, which is something like MPI integer, is of type MPI data type. The communicator is type MPI com. In Fortran, at least in the Fortran 90 interface, these are just integers. This is a pseudo syntax to say that this buffer can be any type, any array of any type. This is where the confusion arrives. This is illegal Fortran, at least in Fortran 90. It is illegal in Fortran 90 to have a function which takes a data type, an argument of arbitrary data type. So I'll talk about this later, but we just forget this. We just tell the, don't bother. Fortran C has void. Void means I don't care. Fortran is a lot more pedantic, a lot more strict, and it doesn't have void. So that causes problems. So this is kind of a pseudo syntax, but just trust me, it all works. Okay. So let's see a real example to make it more obvious. So MPI send, we'll cover that on Monday. MPI send is a non-blocking send. What that does is MPI send initiates the send. I stands for immediate. It initiates the send and gives you a ticket, a request. It's called you have to remember. And later on, you can come back to MPI and say, see this send I issued a while back, has it finished or not? And that allows you to, we'll see that with these routines, especially synchronous send and receive, it's easy to get deadlock. The way you avoid deadlock is to use non-blocking communications, which are the I send, I receive. So that they're called non-blocking calls. I'll cover them in a lecture tomorrow. Not tomorrow, Monday. Is that okay? Yeah. So so we'll see an example here. Of course, this is the prototype. It's not what you type. What you type is something like this. So I want to send data from rank 1 to rank 3. So I have an array of 10 integers. In my code, I do index 10. This is just a C program. Then I say MPI send. Okay. Destination, I want to send it to rank 3. Okay. And the tag is extra information you can put on a message. So a tag is like it's like when you get bills, they come in red envelopes. So you have red messages and white messages. A tag is just extra information you can add to a message, and it may or may not be useful. We'll come back to it later. But the destination is we want to let's send X, which is 10 integers, to 3, and we want to tag the message with 0. MPI send. So I want rank 1 to send data to rank 3. As written, what does that code actually do? I just want rank 1 to send data to rank 3, but as I've written it there, what does that code actually do? I mean, rank 1 may send to rank 3, but other things are happening which we don't want. Who calls the send call in that code as written? Everybody, exactly, everybody. So this code is guaranteed to deadlock, because if everybody is calling the send, by definition, everyone is waiting in the send for somebody to call a receive, but nobody's calling a receive. In particular, rank 3 is sending to itself. Rank 3 is phoning up itself and saying, why am I engaged? Well, because you're phoning yourself. Okay. So how can I get around it? How do I make sure that only rank 1 sends to rank 3? If, absolutely. So what we always end up doing this stuff, if rank equals 1, now this isn't some magic syntax. Every process executes this statement. It just happens to be that if I have set the rank from MPI com rank, if I have done that, then this will have the effect that only one of the ranks issues the send. Okay, so this is just normal code. It's not some magic MPI incantation, but it has the effect that we want. Okay, so in that case, that if you want to send a scalar, C being C, MPI expects a pointer. So if you want to send a scalar, it's int x, you send the address of x, which is 1 int. Okay, so that's just the same thing. Any questions about that? Okay. So in Fortran, it's just the same, except again, array of 10 integers, integer dimension 10x. If rank equals 1, I've used the old syntax. Call MPI send x, 10 MPI integer, not MPI int, 30 MPI com world I error. Fortran, unless you're a real Fortran purist, a scalar is just an array of length. Fortran always passes by reference, never by value. So in Fortran, you can just send x 1 integer. You don't have this pointer stuff that you have in C. So C and Fortran, very simple. Well, why wouldn't it be efficient using an if? Wow. So yes, why isn't it efficient? You're doing an if on a scalar. Why is the code hanging? So I don't. Okay, so that's interesting. Why do you mean the code is hanging? So we look at this code here. So that's a good point. Well, how long does it take to evaluate an if? Less than a nanosecond. I mean, you're clocking at gigahertz. Yeah. An if on a scalar takes less than a nanosecond. This send is going to take 1,000, 10,000, 100,000 times longer. So a function calls tens, hundreds of cycles. So no, the if is the if is for free. It's going to take a quarter of a nanosecond or something. So no, it doesn't matter. Okay. So and there isn't, well, even if it was inefficient, there's no other choice. There's no other way of doing it because the compiler doesn't know about MPI. Okay, the compiler doesn't know about MPI. Okay, receiving a message is slightly different. Receive buff, count, data type, source, tag, com, and status. So in C, this is your receive buffer, and you want to receive 5 integers from somebody with a particular tag within a communicator. And this status, you pass in C, the status is a structure, and you pass a pointer to it. This is where Fortran differs, at least in the Fortran 90 interface. Again, when MPI was defined back in the early 90s, Fortran didn't have structures or derived types. So Dilhan's asked in the Fortran example, if I set the array size I'm sending to 5, say, will it pass the first 5 elements in the array? So that's a very, very good question. So yes. So can I just come back to that? I'll just finish. Well, no, I'll do this. Can I finish this send first, and I'll come back to your question? Yeah, that's a very good question. Yeah. When Fortran 90, when MPI was defined in Fortran 90, there were no structures. Fortran now calls them derived types, in Fortran. So the status here is a little array, integer of size MPI status size. So in C, the status is a little structure of type MPI status. In Fortran, the status is a little array of size MPI status size. This value is defined in the header, but it's a small number, 5 or 6, I don't know. Maybe it depends. Okay. So let's do a real example. I want to receive data from rank 1 on rank 3. Okay. So again, I do int y10. This is where I want to receive the data. MPI status. Again, as written, that doesn't receive data from rank 1 on rank 3. I have to put an if. Sorry, that's the source. That's the tag. And I do if rank equals 3. MPI receive y10 integers from 1 tag 0. So this is a requirement. I'm saying I'm going to wait for a message from source equals 1 with tag equals 0 in MPI com world. If there's a message from somebody else, I ignore it. If there's a message with the wrong tag, I ignore it. If there's a message in a different communicator, I ignore it. Okay, so these are requirements. It must come from rank 1. It must be tag 0. Luckily, it works the way we've done it. And then the equivalent for the receive for a scalar is just the same thing here. Okay. For Fortran, it's just the same, except, well, slightly different. Integer dimension of 10. Why? The status is an array of size MPI status size rather than a structure, but the rest is just the same, exactly the same here, with the IRA variable on the end and MPI integer, but it's exactly the same syntax, except it's simpler for scalars. So, so Dylan was asking about the Fortran example. So imagine I wanted to send, okay, so imagine I wanted to send, yes, if I did, same in the C example, if I did MPI send of, sorry, I've got the wrong slide up here. Apologies for that. If I did MPI send of x5 MPI integer integer, it would send x of 1 to 5. Well, no, wrong. I've done x 1 to 5, not 1 to 4. In the Fortran example, yes. So as Dylan, if I set the array size, I'm saying to 5 to pass the first 5 elements of the array. Yes, it will. Okay. That's, and what? How would you send elements 6 to 10 then? That's the question. So or in C. Okay. So in C, I could do MPI in C or Fortran. How would I send not the first? So if I do MPI send of x5, it sends the first 5 elements. So in C, in Fortran, Matthew's example, x65, x6. What about a C programmer where it gets a bit anyone? So that you're absolutely right for the Fortran questions. For a C example, address x5. Exactly, absolutely. Or if you're being brave, x plus 5. But I actually much prefer Matthew's syntax here. So that's all fine. Now, someone said if speculative execution, I don't think that you can't speculatively execute a function call, because speculative execution has to be reversible. So you can't reverse a function call. A function call could do anything. So there's no way a compiler can speculatively execute a function call, because speculative execution is doing a couple of additions or something. But you have to be able to roll back speculative execution. And so you can't speculatively execute a function call, I don't think. It's just, yeah. Speculative execution can only go so far, and then you run out of, when the send data and receive haven't the same dimensions. No. So this is the point. Mohamedou has got a question. No, because you see, MPI doesn't know what the dimensions of the thing are. All you're doing is, this is where the C program has got an advantage of the Fortran. You're just passing a pointer. MPI actually MPI thinks all the arrays are vectors or one-dimensional arrays. Yeah. In fact, it's not an error actually. You can send an array of length 10 and receive an array of length 5 by 2. As long as they have 10 entries, it will probably work. So it's not an error because MPI doesn't know what the arrays. It doesn't know there are arrays. All it gets is a pointer to the first element, or equivalently, MPI thinks that all your data types are one-dimensional arrays or vectors. Does that make sense? It's a good question. Okay. Again, if MPI was part of the language in the compiler, yes, you could imagine it checking that, but it's a library, so it doesn't know that. So the receive, okay, what this does is it receives the data, the 10 elements into Y from, and this will work, okay, and we'll talk about the stages later. Now, here's a very interesting question, and it's really, I'm glad that Dilhan asked their question. What do you think this 10 means? I'm not a trick, it's not obvious at all. What does that 10 mean? Or equivalently, what do you think would happen if we send count of 5 but did a receive of Y10? So imagine we did what Dilhan suggested. We just send 5 elements of X, but we do MPI receive Y10. What do you think happens? It's not obvious at all, but and a lot of people don't. Do you want to have a guess? So what does that 10 mean? So, okay, so James says, would it wait for more elements? That's an interesting point. So a lot of people think that, but it's not. MPI, okay, so Matthew and Alejandro say 10 bytes, but 10 what? What do you really mean? Okay, so you've covered all the bases there. They're all sensible suggestions. So James's is a very interesting one. No, so MPI doesn't, some people think MPI has like a pipe model. You've opened up a communications pipe, but MPI matches a single send with a single receive. So one send has to match one receive. So it can't wait for more elements because you would have to issue it. So that's, you could imagine a protocol where that's true, but that's not what happens. So Amir is right. It just fills the first 5. So this 10 is not the size of the incoming message. A lot of people think it is, but it isn't. What this is technically saying is, I want to receive data. I want to receive some integers from source 1 with tag 0, and I have reserved enough space for there to be 10 integers, okay? But as Amir says, when it comes in, all that happens is it fills the first 5, okay? So what do you think happens if the incoming message is larger than 10? So Amir is absolutely right. If you get an error, actually, because MPI says you get an error. Again, it's not obvious at all. You get an error. Well, you don't get a memory error. You get MPI. MPI will say the incoming message is too large. But the question here is, so that receive can in principle match any send which has fewer than 10 elements. But clearly I need to know how many elements were received, because otherwise I don't know which data is valid. So how do I find out how much data is received? Where do you think that's stored? So if the sender only sent 5, this receive would complete successfully, but clearly in the next line of the program, I know that I've only received 5, that only the first 5 are relevant. Absolutely, the status records that information. Yes, you could embed that in the tag. That's a good point, but MPI does it for you. You could embed it in the tag, absolutely, but you don't need to. It's done automatically. So in synchronous blocking message passing, and process is synchronized, the sender process specifies the synchronous mode, blocking both processes wait until the transaction is completed. For a communicator to succeed, the sender must specify a valid destination rank, the receiver must specify a valid source rank, the communicator must be the same, the tags must match, the message types must match, the receiver's buffer must be large enough but not exactly the right size, and the question is, how do you... So you might now say, this looks a bit weird, because for a message to be received, the communicator and the tag must be the same. Well, what's the point then? First of all, that's double counting. If the communicator tag, and secondly, what's the use of a tag? If I have to, this is saying I need to know what a tag value is before I can receive it. Yeah. So if I don't know what the tag is, how can that be useful? So Dilhan said you can embed the message size in the tag. You could, but how can you know what tag value to specify when you don't know what the length of the message is? Well, the important point is you can wildcard. So you can receive from any source with MPI any source. You can receive with any tag from MPI any tag. And the actual source and tag are returned in the receiver's status, as is actually the size of the message. And the important point about communicators is you cannot wildcard on communicators. Communicators are an absolute guarantee that the message cannot leave that group of processes. But source and tag you can wildcard on. So is that clear? When you do a receive, not when you do a send, you have to send with a specific tag, you have to send to a specific destination, but when you receive, you can wildcard. So that sort of that kind of metadata is like the envelope information. You know, you have the sender's address and then the data. So basically the major payload of the messages is all the data, but we have all this envelope information as well. And this is returned in the status. So in C, the source and the tag are directly addressable as elements of the structure, status.mpi source, status.mpi tag, or in Fortran, remember it's an array, status. So what this is saying is MPI status size might be 6, so the status is an array of 6 ints, and the source might be stored in the third element, and the tag might be stored in the fourth element. All that depends on the implementation, but that's the way it works. For technical reasons, you cannot, the count, the size of the incoming message is not available directly in the status. You have to pass the status to a helper routine called MPI get count. So what you have to say is, you have to pass the status, you have to do something like MPI get count status, MPI integer, and it will tell you how big that message was in integers. This is due to the technicalities of derived data types, which I'll cover later on. But you can think of it as imagining that actually MPI only knew that it received 16 bytes. And that could have been 2 double precisions or 4 integers or 16 characters. That's not exactly true, but it's a reasonable thing to think. So for technical reasons, the size of the incoming message, the actual count, is not stored directly in the status. You have to pass the status to helper routine, say, I received this message, tell me how long it was in terms of integers. MPI really tries not to talk about bytes because that makes things non-portable. Once you start talking about bytes, you've got non-portability. So MPI has this helper routine. Again, same in Fortran as well. So is that clear for everybody? It's not trivial. So don't, this is not, and a lot of people write MPI programs and never think what happens if the send message is larger than or smaller than the receive buffer. Things like that are actually interesting questions. But where you could use the tag is, imagine that we have a controller worker situation. So I have sent you all out. I'm the controller. Let's say I'm the controller, and I've said all of you have received a message from me with some work. Okay, so I've sent you all, do this work, please. I don't know how long it's going to take. Then I want to receive the first message that comes in. Well, then I can do an MPI receive with MPI any source. That means that when the first person that finishes and sends me the data, I receive that message. I receive your data. I look at it. Who is it from? It was from rank 3. I could then send a message back to rank 3 saying, here's more work. But the difficulty there in that task file model is how to tell people to stop. How do I tell rank 3, actually, I don't have any more work for you, please stop? Well, I could tag the messages. I could have a message tagged 0 might mean this is some work, please do it. A message tagged 1 might mean this is actually the last. This is some work, but it's the last one I'm gonna send you, and that would mean that when you receive data from me, the workers would do a receive with MPI source with source equals 0 me, but tag equals MPI any tag. And when you receive the message from David, that's fine. But what's the tag? It's 0. Okay, that means I need to process this data and ask him for more. Or if it's 1, okay, this is the last one I ever received. I process this data and finished. So tags can be useful for passing extra data. However, in practice, they tend not to be used in MPI. That actually, just when you write real programs, they tend not to be useful. But that's just, we can discuss that later. The final thing I wanted to talk about was, I have some more slides on this, but I'm just going to say, so message order preservation. Messages do not overtake each other. This is true even for non-synchronous send. So messages don't overtake each other is meaningless for synchronous send. It's saying if I phone somebody, then phone somebody else, what order are those phone calls received in? Well, of course they're received in order, because I can't start the second phone call since I finished the first one. But the question is, if I send 2 letters to somebody, if I'm on holiday in the USA and I send my mother 2 postcards, okay, but do those postcards arrive in the order they were sent? Does the Postal Service guarantee message order preservation? Yes or no? So if I send 2 postcards to my mother, no, it doesn't. However, MPI does. MPI guarantees that even if you send things asynchronously, then they will arrive in the right order, and that they'll be received in the right order. And that's not trivial, because of course at the hardware level, this data is split up into packets, can take different, so at the hardware level, the messages may overtake each other, but from a programmer's point of view, MPI guarantees if you issue a receive, if you issue 2 receives, you'll get the messages in the order they were sent. And actually, if that wasn't true, it would be almost impossible to write a correct program, because I could send you a message saying here's some work, another message saying could you please stop, and you get them in the wrong order. So although people don't often think about it, message order preservation, which is a key component of MPI, is almost essential to write correct programs. Now, it's slightly more subtle than that, and I have some slides here, but it's really beyond. I'll skip over them. It's slightly subtle with wildcarding, but basically, if a receive matches multiple messages, so I'm thinking of there being an inbox. I'm thinking that messages come into an inbox. That's a useful model. If a receive is multiple messages in the inbox, then the messages will be received in the order they were sent from the same source. It's only relevant for multiple messages from the same source. It doesn't say anything about 2 messages sent from different sources. They can overtake each other, but that doesn't matter because they came from different people. So normally I normally do this in a phase class. I do this I would do lecture, practical, but I'm experimenting with doing lecture, practical. So the exercise is the calculation of pi. I will go through this in a bit more detail after the next lecture, but we're going to do a pi example. I won't go through that now because we should take a break, but I'm happy to take any questions. But if there aren't any questions, we'll come back. Let's have a 10-minute break, and I'll start again at 10 to 3. Is that okay with everybody? But please ask questions if you have questions. So actually, something I sometimes ask at this question. Imagine I wanted my mum. So I'm sending postcards from the USA to my mum. How can I make sure she reads them in the order they're sent? I might want her to read them in the order they were sent. How can I achieve that? So put a note exactly. So number them. Yeah, exactly. So yeah, but just think of your postcards. But how would I number them? So J. Scott, I don't have your first name here, but it's correct. We can number them, number my postcards. But what number? What would I have to do? You're absolutely right. But what numbers would I choose? So date and time doesn't help, okay? Because my mum gets a postcard from me. It's dated 3rd of June. How do I? Yes, sequential numbers. I number them 0, 1, 2, 3. So if my mum gets a message from me that's number 4, she can look and say, but the last one I received was number 2. That means there must be a number 3 in the post. I'll wait for that to arrive. So a monotonically, well, actually, a sequentially increasing tag, if you want to call it that way, can be used to maintain message order, but not the timestamp, because that doesn't help her. She gets a message and said, David sent a message on June the 3rd. Maybe he sent one on June the 2nd. What does she do? Wait forever till one? It does. So it has to be a monotonic, what? 0, 1, 2, 3, 4, 5, 6, 7 going up the way. And that's, I don't know if that's how the hardware does it, but anyway. The explanation of the MPI modes, send, bsend, and send, the meaning and use of message tags, and the rationale for communicators. These are all commonly misunderstood, but it's essential for all programs to understand the modes, because the fact that MPI send can be either synchronous or asynchronous, which are fundamentally different things, causes a lot of confusion. It's often useful to use tags, and certain cases can benefit from multiple communicators, but it's this MPI modes that I will spend my most time on. So MPI send is synchronous send. It's guaranteed to be synchronous. The routine doesn't return until the message has been delivered, like making a phone call. Bsend, buffered send, is guaranteed to be asynchronous. The routine returns before the message is delivered, like sending an email. The system copies the data into a buffer and sends it later on. MPI send, standard send, can be implemented as synchronous or asynchronous, and this causes a lot of confusion, and that's what this lecture is largely about. So let's do the anatomy of send. So MPI send. Time is going down the way here. We have process A and process B, and process A issues in some abbreviated syntax. I want to synchronously send my variable x to B, and at that point process B is running some other non-MPI code. So at the point when process A issues the send, synchronous send, process B is doing something else. So what happens? What does process A do? What happens to process A at that point? It waits, exactly. So what happens is process A sits in send, just sitting, spinning around. Hopefully, and it would sit there forever and ever, or in practice until your batch job ended. That's one of the reasons we put limits on batch jobs, so that they get killed with deadlock. But in principle, wait forever. But hopefully, if we've got a correctly written code, process B at some point issues a receive, saying, I want to receive data from process A, and I'll receive it into Y. Okay, that's fine. That's good. So at that point, the data transfer can happen. It's called synchronous send because there's a synchronization in time, and the data is transferred from X to Y. And then at that point, there's a synchronization. Send returns and the receive returns. When the send returns, the important point is I can now overwrite X. I can overwrite X because I know it's been delivered, so I can reuse that buffer. And when the receive returns on B, we can now read the value of Y because we know the receive has completed. So that's relatively straightforward, hopefully. But you might worry about this wait. Okay, there's all this waiting about. Someone asked early on, why might asynchronous send be better? Well, we've got all this waiting. So let's see what happens with asynchronous send. Let's do MPI B send. So process A issues a B send. This process B is running some other non-MPI code. What happens here is that the data is copied in some internal buffer, and then immediately the B send returns. But still, the X can be overwritten by A. When a send operation, doesn't matter which one it is, completes, it means that you can overwrite the send buffer, which is good. You can reuse the data, so you can carry on. Process B, at some later point, issues a receive. The data transfer happens at that point. Presumably, the buffer is freed up, and then Y can now be read by B. So we've achieved exactly the same thing, except process A didn't have to do all this waiting around. And also, in this case, if process B didn't issue the receive, at least process A wouldn't deadlock. So this seems like the right thing to do. So you might say, well, why aren't all sends asynchronous? Okay, why would you ever pick synchronous send? The problem is, so first of all here, receive is always synchronous. So the reason I drew, this is what the problem with animation, The reason that I drew process B being slower than process A is that if process B issued the receive before process A issued the send, then S send and B send would largely look the same, because when they posted the send, the receive would be there, so the message would be transferred. So that's why I drew it this way. I pretended that process B was slow and process A was quick. Okay, that was just that. Now this is where animations start to kill you. We'll have to dance back to our. Okay, so receive is always thinking if the process B issued the receive before the B send from process A, then B would wait in the receive in both cases, okay, until the B send was issued. But the question is, where does the buffer space come from? So, you know, it's a bit technical, but MPI has to guarantee that it uses a finite amount of resources. MPI is not allowed to eat up an infinite amount of, so MPI cannot guarantee to buffer any message you give it. Okay. In other words, you have to be able to. It's a slight technical point, but you have to be able to constrain the memory usage of MPI. At least it has to be finite. And so what they said is, okay, for B send, it's up to the user to provide a single large block of memory. So what happens is, if you're going to write a program that uses asynchronous sends, which are B sends, it's up to you at the start of your program to allocate or malloc a buffer of 10 megabytes or something. Then you give it over to MPI and say, there's a routine called MPI buffer attach. So this is all getting rather horrible. You say to MPI with MPI buffer attached, here's 10 megabytes. Whenever you do B sends, yeah, then I want you to store the data in this buffer. And that seems fine, okay? So you've given it some memory here by some previous call, right at the start, MPI buffer attach, here's 10 megabytes, store the data there. But what can I do immediately after calling this B send? Okay, what else can I do? I've done one B send, what can I do immediately after that? If I'm going to send 10 megabytes of data, I could do another B send, and another one, another one, another one. I don't know when process B is going to issue the receive. Process B might be having a bad day, might be being slow, okay? So the problem is, it can be quite difficult to actually bound the amount of data you want to give. And so although you would like messages to be buffered, to be asynchronous, it's quite hard. And the problem is, if A issues another B send before the receive, the system tries to store the message in the free space in the buffer. But if it runs out, then B send will fail. And this is the worst kind of program. You could have a program that runs 99 times out of 100, and then one time you run the program, process B is very slow, you issue an extra send and you run out of memory, storage space, and it falls over. Now, sometimes you can bound that. Sometimes you can look at your program and say, there can never be, because of the logic of this program, there can never be more than 4 outstanding B sends. So then I should, this is where B send gets even more horrible, okay? So imagine that my messages are 1 megabyte, and I can reason there will never be more than 4 outstanding B sends. So there could be 4 outstanding messages of the size of megabyte. How big does my MPI buffer attach have to be? 4 megabytes? A bit bigger, maybe? In one think of the problem. So I want to send 4 messages, each of a megabyte. How much storage space do I need to reserve to buffer those messages? Is it 4 megabytes or more? And why might it be more? When I send a message, more than just the data is sent. The envelope. I have to reserve a bit more. Well, Helen's right. It does depend on how many copies are made. That's a very good question. But if you look in the MPI, that's a very good point. If you look at the MPI standard, I think it guarantees there's only 1, but more. So you have to add 4 times the metadata overhead, which is some magic number called MPI B send overhead. I can't remember. In practice, people do not use synchronous send in MPI. It's very unusual to see people using B sends. It's not an elegant way to program. And the rationale is, look, don't tell MPI to use synchronous send. Don't tell MPI to use asynchronous send. Tell MPI to use send and let it choose what it thinks the best is. So that's the rationale. Okay, use MPI send and let MPI choose to do it synchronously or asynchronously. So what MPI actually does, now in principle, MPI could choose on Mondays, Wednesdays, and Fridays to do synchronous send, and on Tuesdays, Thursdays, Saturdays, and Sundays to do asynchronous send. Now, of course, that isn't what it does, although it would be legal or a bit annoying. What it actually does is, so here's the problem. SSend runs the risk of deadlock. We saw that. BSend is less likely to deadlock, and also your code may run fast because you don't all just waiting around. But the user must supply the buffer space. The routine will fail if this buffering is exhausted, and fail means crash. So MPI send tries to solve these problems. There is buffer space provided by the system, not provided by you, a finite amount of buffer space that an MPI implementation will reserve. And send will normally be asynchronous, like bsend. However, if the buffer is full, send becomes synchronous, like ssend. So if you do when you call MPI bsend, you are mandating to MPI it has to do an asynchronous send. If it doesn't have enough buffer space, it crashes, so they can't do it. MPI send is basically saying, could you please try and do an asynchronous send? But if you can't, then just do it synchronously, so you don't need to buffer it. So MPI send routine is much more unlikely to fail. But the big mistake people make is they assume that MPI send is asynchronous. You don't know that. It will typically be asynchronous for small messages, synchronous for large messages, but you don't know when the switchover is. And this is the biggest mistake people make. People assume MPI send is asynchronous. So they write this code here, okay? Process A issues send of X to B. Process B issues send of Y to A. Process A receive XB. Process B does receive YA. This code is not guaranteed to work, okay? It will deadlock. If this was ssend and this was ssend, it's really, really important to realize if both of these are ssends, this code is guaranteed to deadlock. Because process A is saying, I am going to wait for process B to issue a receive because I'm using synchronous send. Process B is waiting for process A to issue a receive, and neither of them get to the receiver. You're in this catch-22. You're both phoning each other and saying, why are they engaged? So this code is not guaranteed to work. It's guaranteed to deadlock if send is synchronous, send. Therefore, it might deadlock. This code might deadlock. You don't know. For small messages, you're probably okay. For large messages, you're probably not. So this is the problem, that when you program with send, although MPI may try and help you by buffering the message and being asynchronous, you always have to have in the back of your mind, send might be synchronous, I need to work. So how can I get this code to work? How can I get this exchange to work and be guaranteed to work? So you should always think to yourself when you use MPI send, what would happen if it was implemented as synchronous send? There is a way to get this to store process B's Y to another variable. No, I don't quite understand. That wouldn't help. The problem is they're both trying to send and receive the other one. You might have, I don't quite understand that. Sorry, Matthew. I don't quite. Yes, swap send and receive and one exactly acts as God. So process B, yeah, sorry, you were saying the same thing. Apologies. Yeah. So process A does send and receive. Process B does receive and send. Now that works here, but in general, that can be quite hard to yeah. So you've got send, receive, then B is received. Exactly. That can be difficult to work out in more complicated. In this simple pairwise swap, hey ho, it works okay. But in general, it's much harder. So to avoid deadlock, we either match sends and receives explicitly, and this is like a ping pong. Process A sends, then receives. Process B receives, then sends. For a more general solution, you have to use non-blocking communications. And the reason you can use non-block communications is that you can say to MPI, please start this communication, be it a send or a receive, return control to me, and we'll come back later and see if it's completed. So, but the reason you should program with ssend, so you've got an interesting question. Do send and receive match only by the tag? What do you mean by that? So I've used an abbreviated syntax here. I've assumed that the tags are matching here. What did you? So this receive will Well, send and receive matches fundamentally by sender and receiver. They match a sender and a receiver. Let's assume we're not using tags. Let's say everybody specifies tag 0, okay, for example. In that case, a pair is, a sender and a receiver match. That's how so the fundamentally send and receive. So you have to set an explicit destination. So from the send side, you're sending to an explicit destination, and then when the receive issues a receive, that matches up as a pair. That answers your question. So tags, typically people don't use tags. They specify 0 for the tag all the time. That's a standard way of programming. And so therefore the pair is a sender and a receiver match each other. And if there's more than one, there's multiple communities, they match in order. Yeah. So so this is actually, I skipped over but if the sender sends 5 messages to the receiver and the receiver issues 5 receive, they match. The first send matches the first receive, the second send matches the second receive. They match in order. Okay, that's a good question. Does that answer your question? So if there's multiple communications between sender and receiver, then they're matched in time order. Yeah. Okay. Yeah, fine. So you're right. If we didn't have message order preservation, we'd need to use tags to disentangle that. But it's because we have message order preservation that we tend not to need tags. Because if I do 5 sends and there are 5 receives, they're guaranteed to match in the order that they were issued. Yeah. So that's good. So you should always, in this course, you should program with send, because if you program with send and you make a mistake, your program deadlocks. It's guaranteed to deadlock, which is what you want. We want incorrect programs not to run. The worst thing that happens in the world is incorrect programs running. So what you should typically do is program with send. However, when you actually run in production, convert all your sends to sends, and your program might go faster. Okay, but remember, you have to always remember that send could be implemented as synchronous send. So send is allowed to be send. So for learning MPI and writing correct programs, you should program with send. It's much more likely to pick up bugs such as deadlock than send. But then when you actually implement your program, you run it in practice, you can convert all the sends to sends, and it probably would go faster. So it's unfortunate we have to go over all these details at this point, but it is really one of the most annoying points of MPI and the one of the most commonly misunderstood. The MPI send can be synchronous or asynchronous, and you don't know which. The other thing which isn't obvious, but turns out to be the case, is people just don't use MPI bsend. I've very rarely seen a code that uses explicit asynchronous. People use send, and then you say, well, how can you use send when it could be synchronous? How do you avoid deadlock? Well, you use non-blocking communications, which achieve the same thing as asynchronous, but without needing buffering, which I'll cover those tomorrow. Are there any questions on that? If not, you may need to take a while. Can it be said there's STM receiver issues a barrier for the set? In some sense, yes, although in MPI speak, a barrier is global. So a barrier in MPI speak would be a barrier across all processes. But it's a synchronization for the sender and receiver. An send receive pair, you can guarantee that at some point, like a phone call, they're both actively participating in the send at the same time. So it's a mutual synchronization, like a handshake. I wouldn't call it a barrier, because a barrier in MPI is a more global thing. A barrier would synchronize all processes, but it is like a mini barrier for the sender receiver. Yes. Yeah. Okay. So a lot of people at this point say, well, oh, okay, sorry, I missed that. Yeah. So if the tags for the sender and receiver are different, while all the parameters match, will the send wait until another matching receive is found? Yes. Yes. So actually it will wait. Absolutely, it will wait till the matching receive happens. So when a send or receive completes, it means that everything happened successfully. That's a very good question. So that message order preservation talk is you may want to have a look at it, but it kind of goes into these issues. It's hard to do. In the face-to-face course, I do a little game where we have people pretend to be senders and receivers, which I think issues it. It doesn't work so well on slides, but you're absolutely right. So it's the first thing. If the send waits until another matching receive is found, that's exactly correct. We'll say there was a receive, wrong one, ignore it, and waits until the correct one comes in. Does that answer your question? Sorry, I didn't notice your question because I got too many beeps at the same time. That's my fault. Is that okay? Yeah, okay, good question. So at this point, some people say, how can I receive messages of arbitrary length? Because you've just told me when I issue a receive, I have to specify a buffer, but I don't know how long the message was till I've received it. If the incoming message was too long, it will fail. There's a thing called probe. MPI probe has the same syntax as receive, but no receive buffer specifies. MPI probe says, if I were to issue a receive at this point, don't receive the message, but give me the status. And what you can do is you can find out who the message would come from and then specifically how long it is. So if you have a program where you don't know how big your messages are, or you can't even have an upper bound on your message length, you do MPI probe, MPI get, count, malloc, receive. So there are some technicalities if you use wildcarding, but the important point about probe is, so be careful with wildcards. If you use wildcards in MPI probe, if you do a probe with MPI any source, when you do the receive, you have to do a receive with that specific source. If you do MPI probe any source, MPI receive any source, it's not guaranteed they will match. So you have to do MPI probe any source, MPI receive status.mpi source. It's a slight technicality. But the main thing is probe allows you to say, if I were to receive a message, issue a receive here, what would I receive? And then that allows you to do things like then allocate enough space for that message to come in. Okay. So tags, every message can have a tag. It has to be a non-negative integer value. It has to be non-negative because well, we have this value MPI any tag. Okay, this is just a number defined in the header. How can the MPI libraries tell if you're specifying a user tag or the special value MPI any tag? What do you think the MPI any tag value is? I tell you to write a library, it's going to take a -1. Yeah, negative number. It might be -5, but it's negative. So this, he says, like, user tags have to be non-negative, and it allows the system to specify these things. It's slightly complicated. MPI guarantees support tags of at least 32767, which is 2 to the something -1, isn't it? In practice, most implementations allow you to have much larger tags than that, but they cannot be arbitrarily large. So some implementations allow you to have tag values up to 2 to the 32 -1, 2 billion. So the main thing is they cannot be arbitrarily large. You know, there is a way of finding out how big they can be, but you should just not. You shouldn't assume they can be arbitrarily large. There's some advice in the standard, but tags are only useful if you do wildcarding. Without wildcarding, tags are useless, because if I send a message with tag 3, the receiver has to know the tag is 3, so I've not done anything. So they're most commonly used in MPI anytag, but actually, because of message order preservation, most MPI programs don't use tags. You have to specify, so you just have a global default of 0, for example. I use them occasionally, but in practice, message order preservation typically helps you here. Communicators, all MPI communications take place within a communicator. A communicator is fundamentally a group of processes. The predefined communicator MPI com world contains all the processes. MPI com self, which only contains you. So MPI com size of MPI com self is 1. MPI com rank of MPI com self is 0. The important point about communicators is the message can only be received within the communicator from which it was sent. It's not possible to wildcard on com. So it's an absolute guarantee of in some sense, separation of messages. And there's a couple of uses for communicators. One is the obvious one. You can split MPI com world. So Queven's made exactly the right point. A common state permits set the tags equal to the iteration number. That's exactly, I should have said that. That's exactly the point. What the MPI standard says is that if you run on the tag should always be allowed to be as big as the number of processes, probably. So if you can run on 1 million processes, you should be able to specify tags of up to 1 million. But exactly as Queven says, then they can't be. You said the iteration number is exactly the thing which people do, and then it breaks. That's a good point. To split MPI Comworld into pieces, you can split MPI Comworld into pieces. There is a routine called MPI Com split. You can look up the syntax if you want, but you can take a communicator and split it into two. So I might want to say, look, I want to like split my machine in software. I want the ranks 0, 1, 2, 3, 4, 0, 1, 2, 3 of Comworld to do one thing, and 0, 1, 2, 4, 5, and 6 to do something else. And I want them, when they send messages, to be completely ring-fenced from each other. So what I can do is a routine called MPI Com split. You split a communicator into sub-pieces, and here I've put 4 ranks in Com1 and 3 in Com2. Now it happens here that the ranks in Com1 are the same as the ranks in Comworld, but that's not guaranteed. And in particular, Com2 is of size 3. Your rank is always up from 0 to the size -1. So the ranks in Com2 are 0, 1, 0, 1, and 2, which are not the same as your rank in Comworld. So if you start playing around with subcommunicators, you need to start playing around with ranks. You need to watch my rank in Comworld and watch my rank in Com. So just because rank 1 in Com1 is different from rank 1 in Com2. Just I live at house number 51. Other people live at house 51, but they're not the same house, they're in different streets. So, 51 is a unique identifier in my street, but not a globally unique identifier for my house. But the most important thing about your ranking Comworld is your ranking Comworld is guaranteed to be globally unique. Every process has a separate rank. So your ranking Comworld is by far the most important rank. But if you start creating subcommunicators, you need to compute new ranks. Because if I want to send this guy's rank 6 in Comworld, but rank 2 in Com2. If I tried to send to rank 6 in Com2, MPI would say there's no rank 6 in Com2. It's only got 3 members. How can there be a rank 6? Now you might say I could ring fence messages in this communicator with this one using tags. I'll say these guys will tag their messages with 2. These guys will tag their messages with 1. But that's not a guarantee because wildcarding. You could wildcard on tag, so you could accidentally receive messages in the wrong communicator. So the other thing is MPI was built to be very general purpose to allow you to write parallel libraries. So imagine I've used the example here of a fast Fourier transform. Equally, I could do a sort routine. I've written a parallel sort routine, which takes distributed data and sorts it into order. It does it really fast using a fantastic parallel algorithm. So from the user code, I just do call magic parallel sort routine, and the library does the sort. Within the library was sending and receiving lots of messages. How do I make sure that the messages that the library is sending aren't accidentally received by user code? A user may have issued an MPI receive. How do I make sure the messages in the library? Well, what you do is you duplicate the communicator. There's a routine called MPI com dupe. So the library, the first thing it would do, it would create a copy of MPI Comworld. It would create a communicator which includes all the processes, but it's logically a different communicator. So the messages sent in the library communicator, which includes all the same processes, are ring fenced. It's a parallel communications world. Again, you cannot do that with tags because of the wildcarding on tags, but you're not allowed to wildcard on communicator. So summary, why bother with all these send modes? It's a little complicated. It's unfortunately complicated, but send and bsend are clear. Send is synchronous and bsend is asynchronous. Send can be either synchronous or asynchronous. MPI is trying to be helpful here, giving the benefits of bsend, but not failing completely if buffer space runs out. In practice, this leads to endless confusion. When you call send, the amount of system buffer space is variable. Small messages will probably be buffered. Large messages won't. The buffer limit will be 10K bytes, something like that, but you don't know. Programs that run on one machine may deadlock on another. You should never assume that send is asynchronous. say when you program with MPI send, always think to yourself, would my program be correct if I replaced all the sends with S sends? And if the answer is no, then you have an incorrect program. What are all the tags for? If you don't need them, don't use them. Perfectly acceptable to set all tags to 0. Some people can be useful for debugging, but possibly not. I tend to set all tags to 0. Question, can I just use ComWorld? Yes, many people never need to create new communicators. However, it's kind of bad practice to specify MPI ComWorld explicitly. So, you know, I would much rather have a code which does MPI com rank, MPI com size, and up here has MPI com, or integer for Fortran, and com equals MPI com. This does not create a duplicate of com. This is exactly the same as if I've written MPI ComWorld here by hand, okay? But it has two advantages. One, it looks a lot more elegant because I don't have this horrible, ugly, constant MPI ComWorld here. And secondly, in a year's time, if I come back and I say, oh, I've got 1,000 lines of code here, and now I want it to operate on an arbitrary communicator, not just ComWorld, I've already got that, and I just do com equals com1 or com equals com2 up here, and it works. So actually, as a programming style, this is nicer than putting this horrible, big, ugly constant in your code. But that's just a programming style. So that's really all I had to say, and I'm just going to spend the next 5 minutes going over the exercise. I don't know if anyone had any final questions about that. So I will now briefly show you I need to find the correct I have too many windows here. It's always the problem. So I'll do this more slowly than before just to check it works. So hopefully we're sharing it. So if we look at the exercise sheet, this pi example is by no means quite complicated, and I'll spend the first lecture tomorrow going through in some detail. The important point is that an approximation to pi can be obtained from the following expression. This is one of these. This is some arctan thing, and all I've done is so the fact that this integral is pi by 4 is to do with some. I can't remember, some arctan, you do some substitution, but I can expand this integral, the area under the curve, as a sum of, very naively, it's a series of number of bars. Now, it doesn't matter if you don't. Pi by 4 is approximately 1 over n, sum equals 1 to n, 1 over 1 plus I minus a half over n squared. As you increase n, this becomes more accurate. The important point about this summation is, like all summations, iterations are independent, so we can parallelize. So we could say, if we had two processes, we could say, well, process 1 does I equals 1 to. Now I'll pick n equals 840 simply because it has a lot of factors in it. But so if I have two processes, I could say, well, process 1 does I equals 1 to t, process 2 does I equals 421 to 840. They each calculate a subsum of pi, then I have to add them together. So that's what we're going to do. And so please follow the exercise as you go along. Write a serial code first, okay? Modify help. So each independently computes the value of pi and prints it to screen. They should all print the same value, because C programmers are going to get this wrong. This is 1 to n, yeah? Not 0 to n minus 1, it's 1 to n. So please make sure. Okay, so we're getting issues there. What's the issue? Is it screen or audio? What's the problem? Someone maybe type in. Okay. So it seemed like there was just a. Okay, yeah, it might have been at my end. So if I go back to calculation of pi, this is an expression for pi by 4, this summation. This can be split up in parallel. So if I had two processes and n was 840, now n equals 8, if you give 3.1 for 1593, it should be quite accurate. You could say process 1 or rank 0 does iterations 1 to 420, rank 2 does iterations 421 to 840, then we have to add the numbers together. So the way I want you to do the code is first check you get the right value in serial. It should be 3.1 for 1593, something like that. And C programs will get this wrong. This is I equals 1 to n. Okay, you need to be careful that don't do this division in integer division because you'll get 0. So you need to be a bit careful here. Now arrange for different processes to do the computation for different ranges of I, but just print them to the screen and maybe add them up by hand. So that illustrates splitting up a calculation, and you'll need to know your rank and your size to do that. The rank tells you which portion of the sum to do. The size tells you how much of the sum you should do. And the final, the tough bit is to accumulate these partial sums by sending them to the controller. So all processes except the controller send their partial sum to the controller. The controller receives the values from the other process, add them to its own partial sum using send and MPI receive. And so, it's not a trivial code. You may find it straightforward, you may not, but it does illustrate a lot of about message passing. There are other exercises here. There's an issue on how you time programs. There is some extra exercises. There's broadcast and scatter and ping pong. Exercises 1, 2, 3, and 4 can all be done just with send and receive. But really, the key one is that don't worry if you can't do the other ones. The key one is to attempt the parallel calculation of pi. And because it is such a key example, I will spend the first 25 minutes tomorrow going over, not tomorrow, Monday, going over in some gory detail the solution to this. Now, there are solutions there. There's the detailed solutions to pi calculation, simple example solution to all exercises. That's all there. You can look at those if you want. You'll need to do that funny wget because, well, actually, to download them, I think the way to download them from GitHub is to do raw. Yeah, here. It goes a bit funny. So you have to download them as raw files. Really, GitHub is very annoying. But I recommend that you try and have a go at it yourself before looking at the examples. But I will go through these detailed solutions go through them in some detail. They're rather verbose, but deliberately verbose. I'll go through them in some detail on Monday morning, the first thing on Monday. So that's, if there are any, if I take any further questions, but we'll be back at between 4 and 5 when I think Creven and William will be around to answer your questions. So if you have any issues, even on still logging on to Archer 2 or running jobs, or outside of today, you won't be able to use that reservation. But if you see in the Archer 2 MPI.job, there's a comment to tell you how to use the short queue, and the short queue is what you want to use during the day. I mean, the slight subtlety about using Archer 2 for teaching is that we use exclusive access, so you have exclusive access to a node. That means even if you run an MPI job on one process, you actually use a whole node, which is 128 processes, which isn't ideal for training, but that's the way it is. If you do have MPI on your laptop, you might find development a bit quicker, but hopefully with the short queue, you should get things around pretty quickly. I would recommend debugging on one node, and that was much more likely to go around quickly. So with fewer than 128 processes, just pick a single node and develop that way.